Hey, this is the video for 2.3, Atomic Radius. So go ahead and set up a new entry in your Cornell Notes. Remember to start a new page for this video. Also, check out the essential vocabulary. Today we will be discussing atomic radius, electronegativity, and ionization energy. So the atomic radius, you should know this from geometry, but an atomic radius is simply half of the distance between two adjacent atomic nuclei. What? That's the definition. But really, you can think it's from the nucleus to the outermost orbital. But this is the official definition, but the definition is basically halfway between the center of the atom to the outside of the atom. And the trend in atomic radius, it is small up here and it is large as you move down to the left. This is relative atomic radii for some of the elements, and you notice they're much bigger down here, much smaller up there. And the reason for that, the radius is increasing as you move down a group, and this is because you're adding additional orbitals. So these metals on the far left are going to be much larger because they're adding the orbital, the s orbital, and this is a little bit more advanced than you need to know, but they're adding an s orbital, which is a spherical shaped orbital, to the outside of all of the other orbitals. So it's one valence electron, and I like to use an analogy. Imagine you're walking a dog. You're a dog walker. If you're walking one dog, that dog can walk on a really long leash and not get caught up with other dog leashes because you're only basically handling one dog. But if you're walking a lot of dogs, you can't let them walk on a really long leash because those dog chains are going to get all tied up with one another. So this kind of happens with valence electrons. When you only have one valence electron, it is a very large radius. And then as you move across, you're adding more and more and more valence electrons, and the radius actually gets smaller. And this has to do with the influence of the protons on the valence electrons. Because you're adding electrons to an orbital that is closer to the nucleus than you would see over in groups 1 and 2. And this is, again, college chemistry or AP chemistry that you don't need to understand. Again, think about the dog analogy. Because when you're walking 1 or 2 dogs, you can let them be on a long leash. When you're walking 7 or 8 dogs, they have to be on much shorter leashes. In this situation or this sense, the radius is also smaller. But this atomic radius is actually indicating the trends that you're going to see. And it's going to indicate a lot of this reactivity that you'll see in these elements. This is all found in Table S. Just like electronegativity, but you have the atomic radius, you have electronegativity, and you have ionization energy. That is what I'm going to be discussing today. But atomic radius, all of these numbers are all available to you, so you can literally just look at them and indicate if you ever have to answer questions. But if you understand the trends, that's even better. The trends in electronegativity is it is very low electronegativity down here, very high electronegativity right here. Electronegativity is basically just an arbitrary number, typically 1 to 4, but electronegativity of 4 is the highest. Fluorine is the most electronegative element. And electronegativity is just the ability of an atom to attract a valence electron. And this makes sense because fluorine is a really small atom, and it has 7 valence electrons. It wants to get that magic number of 8. Helium, neon, argon, none of these noble gases have electronegativity values because they don't want to attract a valence electron. They're perfectly satisfied with their octet or duet in helium's case. And likewise, francium, cesium, barium, radium, these are all going to have very low electronegativities because they don't want to attract a valence electron. They want to get rid of their valence electron because underneath that single electron is an octet. So the ionization energy follows this same trend. If you're holding on to an electron or you're attracting an electron, it's going to take a lot of energy to get rid of that electron. So the ionization energy is found in this column, and in this column, helium has the highest ionization energy. And this is because this has an ionization energy because ionization energy is the energy that's required to remove a valence electron. So helium is a very small element, and it holds on to that valence electron. It's very close to the nucleus. It's holding on to that valence electron very, very tightly. It's going to take a lot of energy to remove that first one. Once you get rid of the first one, to remove that second valence electron will not take as much energy, but it will still take a lot of energy. So I hope that this video is informative. I'd like you to respond to this check for understanding. I thank you very much for your attention, and I will see you soon.